Tom from London, UK, a DevRel engineer at Ably, who has interests in open real-time data and ways of representing this and sharing it with the world. Tom is also a member of some amazing open standards, for example, Open API. In today's talk, Tom is going to be talking about streaming GTFS transit data in real time using Node.js. So what's this talk about? Well, let's dig into more details. Transit data is used by many for travel. Most of these sources follow GTFS, but unfortunately don't offer a real-time solution. Those that do tend to do it in intervals, which render it hard to use for clients. So in this talk by Tom today, Tom is going to share the research and how GTFS can be implemented in real time with Node.js. Over to you, Tom.
Hello, welcome to my talk on streaming GTFS transit data in real time using Node.js. Before I get into what any of that means, I am Tom Camp. I'm a developer advocate and engineer at Ably Realtime, where we effectively just help various companies and individuals distribute their data using real-time protocols. And today, the problem I am interested in, and hopefully should have gone through in great depth during this talk, is given some static information about some vehicles, such as the schedule of a bus, where it will be expected to stop at what times, and the rough route it is going to be following, as you can see from these Google Map images. Is there a way to predict where the vehicle will be at any given time, not just when it's at one of the stops, but any time between those points? And really, what I'm wanting to have in order to visualize this and show all of this off by the end is a Node.js server publishing out updates after doing some processing of all of this static information to work all of this out, as well as also having a nice client with a wonderful map on it presenting the live vehicles moving around in real time, just pottering along, and hopefully it'll be quite visually nice. So a bit of context firstly as to why any of this is of interest to me. As part of working at Ably, one of my major focuses has been on promoting real-time data. And when I say open, I mean available to anyone for free, and hopefully can be used for cool projects and just for generally any form of application that someone's interested in constructing. And as part of promoting that, I have been largely responsible for something called the Ably Hub, which is something which is effectively akin to a repository of open data sources where anyone who's publishing data into Ably can open it up to the Ably Hub for anyone else to subscribe to and use for free. And I'm quite happy with it, to be honest. And you can subscribe with WebSockets, MQTT, SC, various other protocols. And as part of that, really one major thing that I've been doing is looking at ingestion of information. So various sources of data which are currently static, not really updating that regularly, and could be improved, let's say, from my perspective, and looking at ways to make it more real-time and make it easier for clients to consume and use using these real-time protocols. And one of the major kind of sectors, really, of open data which can benefit from real-time, in my mind, has been transit data, where transit data is effectively just information about any transit system, so bus locations, train locations, where stations are, what paths they follow, all of that exciting stuff. And thus I was clearly very naturally drawn to that as part of that. So before we begin on my solution, we have to establish, of course, what currently actually exists and what are these transit companies currently using for their static solutions or more. Most commonly, particularly in America and non-UK countries, UK being as specialist as it is, has decided largely to keep away from GTFS, is a specification, general transit feed specification, to call it by its proper name, which effectively is a hosted zip file containing a collection of CSVs, which each CSV containing some information about this transit system. So you have one CSV, which is all of the different trips that a transit system will have, and one will contain all of the stations, all the information about the stations, and all of that wonderful information. This information is usually very irregularly updated. very, in my perspective, as someone who's constantly dealing with real-time data, in that it's once a week minimum, maximum really, where there's many different transit systems I've seen where the regularity of updates is considerably less regular than a week, and it's not exactly going to be very useful for our goal, which is real-time representation of vehicles' position at any time. So the question is, firstly, before we do anything, what solutions exist already for real-time? What can we use that works well with GTFS data? I'll refer to it as GTFS static for now. That will allow us to bring a bit more of a real-time spark to it, a bit more representation delays and all of that. Well, as it happens, there is something called GTFS-Realtime. This updates roughly every minute and has information on delays, arrival times, expected arrival times, changes once a minute, and even for some organisations, they have the actual vehicle positions being transmitted, which is brilliant for all of this. But unfortunately, it's not quite a solution for my goal, which is trying to represent as much of the entire transit system of the world as possible. And that's because, unfortunately, most companies which have GTFS data do not also have GTFS real-time data available. And in addition, once a minute is a lot better than the once a week that we were having with the GTFS static information. However, it's still not that accurate. And equally, as few companies are supporting GTFS real-time data, even fewer then support also the vehicle position updates. So then to actually have accurate representations of a vehicle only once a minute for such a small percentage of companies and transit systems across the world isn't really scalable at this point. I look forward to the day where it's more widely adopted. But for now, what I'm going to be doing is making my own solution to this by, effectively, the goals are taking a static GTFS bit of data into a Node.js server, processing it in some way, which we'll go over, to publish updates into Ably, and then having our lovely map on the end, rendering these vehicles moving about. And in addition, as a bit of a improvement, making use of, where available, GTFS real-time data as well in order to make our maps even more accurate. So firstly, let's go over some of the different files that we're interested in our GTFS static information. So firstly is the shapes.txt, which effectively, if you think back to that Google Maps image at the beginning, the line which was drawn between the two stations you could consider a shape. It's just defining the different nodes which connect together in order to form the shape of a trip, where a trip is also stored in trips.txt, believe it or not, which is just the series of stops a vehicle will travel between. So stops being, train stations and bus stops and all of that. This lets you know what route they're also a part of and what shape they follow, where a route is a collection of stops, collection of trips, apologies. Stops is then stops.txt is just information about these stops and stations, so where they are, their names, what accessibility they have, that sort of thing. Stop times is giving you information on a trip and at what time that vehicle of that trip is going to be stopping at any of these stops. And finally, the last two are our routes.txt, which is letting us know information about each of these routes, which is a collection of trips, as discussed earlier, and calendar.txt, which lets us know which days these trips and routes are being travelled on. And really, to be honest, that's all we need to do the rest of everything we need. So let's say we have a map and we're interested in drawing one of our trips on here. Let's first draw the shape that's attached to that trip. So using the info from the shapes.txt file, we're just taking these Latin long positions and applying it to this map, and we get, as you can see, roughly follows the route that we'd expect it to follow. Thankfully, most sources have slightly more accurate drawings of the positions, so you end up with a much more realistic representation of the actual route. Next, let's apply the stops, which again, just take the stop. It has an ID attached, its position, plop it onto the map. Nice and easy. As we'll see in a second, this does have some complexities in how we actually work out where on the shape a stop is going to be, particularly for the bottom stop. If you can see at the bottom, it doesn't actually intersect with any of the shapes. So that can become a bit of an issue. Definitely one we can solve, but it's worth keeping in your head. Next, we add the stop times, which again just lets us know what time on this trip a vehicle will be stopping at each of these stops. And with all of that, we've kind of got all the information we need. We know, as in just visually looking at it, you roughly know where a bus will be at each of the stops, where they are, and how the vehicle will travel between those stops. So let's just look at a very simple way that we can get this sort of information rendered on a client side. So in this case, I'm going to use Mapbox, which is a really great tool just for trying to render maps and any form of information, stats, etc. that you'd be interested in on that map. So it really is as simple as just linking the CSS, Mapbox CSS and JS files, creating a div with an ID of map, and then just effectively listing out your coordinates, adding that as a source for your map, layering that onto the map, and you get out something like this, where you can see the exact route where it's drawn a line between each of those coordinates you've specified, and you can effectively just apply that potentially for every single route and trip that you're interested in, and you're in business really. And that was pretty easy. The shapes lets us know the route, the stations let us know some times and additional information, great. But before we start using this to work out exact positions of vehicles between all of those stops, we need to consider something, which is where on a shape is a stop. This can often be quite easy, as in if we look at this, it becomes visually quite obvious that, well, not necessarily obvious, but it almost seems certain that it must fall between those bottom two nodes like this, and we can programmatically check the shortest distance effectively, aka what we've visually been looking to see is the closest line, by just simply working out the distance between this stop and the two nodes which make the edges of the line, and then calculating the distance between that, and you effectively iterate between each node pair in order to find out which is the shortest distance, and then insert it in at that point, and you're in business. You've now got effectively a list which you have representing the entire route of a trip, including the stops, which will be extremely useful for trying to predict the position of a vehicle. It's not always that simple. Sometimes you end up with something like this, where, let's say, the trip has the vehicle backing on itself. Perhaps, it gets to the end of a road, it has to come back, and this return route is going to actually end up coming closer to the stop, even though it isn't the actual stop that we're interested in stopping in at that time. There are two solutions to this. One is something inbuilt into GTFS, which is distances travelled, which for every single shape and also every stop in a trip, there's an optional field where you can specify how far along the shape the vehicle has travelled to get to this point. And using this, if it's available, it's really easy. You literally just have to compare the distance, work out which two nodes the distance of the stop falls between, and then insert it there. So here, very clearly, the 50 falls between 0 and 100, and the 150 of stop 2 falls between 100 and 200, so we can insert them into the relevant locations. This is a bit problematic if we don't have that. We have to use some form of contextual information, such as if we attempt to insert a stop at a certain point, is the next and prior, does the position of the next and prior stop make sense given that context? For example, if we ended up inserting stop 1 at the very end of the route and there's still 10 more stops to come and none of them are near to this final point, then we've clearly placed it in the wrong point, and so we should back along through the whole process and attempt to try and find out a next best shortest distance and then attempt that insertion again. But this is all certainly solvable, not necessarily simplistically and 100% reliably, but you can almost certainly always rely on something to be fairly accurate, especially if you have these distances involved. Next is, of course, the actual magic, which is we have created our wonderful little node network, node line, where we've got the stops and shape geometry positions all inserted together, and we know the distances of them because either we've been provided them or we've calculated it as part of our prior step, and we know the times that a vehicle is at each of the stops. And from this, we now want to say, okay, where is the vehicle in this given the time is 10:05? What is the coordinates of the vehicle? And just eyeballing it even, you can be quite certain that it is going to be between stop 2 and stop 3, because stop 2 has a time of 10 o'clock and stop 3 has a time of 10:10, and if the current time is 10:05, surely it falls into that region. Usually, very mathematic, in a programmatic way, you can easily calculate this as well, just by iterating through the different nodes until you find the point where your stop exceeds a time prior, the stop's prior time, and the next stop's time is after the current time that you're interested in. Once you've got that, we need to work out roughly how far between the 2 points we expect it to be. And given the only detail we have about our current vehicle's position is the time, that's what we're going to use. So we can make a naive assumption at this point, which is that the vehicle is going to be travelling at a constant rate between the 2 stops. We know when it starts and when it stops, and that's all we know. So with this naive assumption, which we can improve on in the future, which I'll cover in a bit, we can say, okay, well, it is halfway between the 2 stops based on time, so let's assume it is halfway through in terms of distance as well. So once we've worked out it's 50% of the way in terms of time, let's apply that to the total distance between the 2 stops, where now we've worked out that it is 150 distance between stop 2 and stop 3, and we can then say, okay, well now 350 distance, which is the summation of 200 to 150, falls between those 2 nodes of distance 300 and distance 400 in this little section here. So given that, where between those 2 nodes is the vehicle going to be in terms of coordinates? We know its position in terms of distance, but we don't know it now in terms of coordinates. Well, again, we can do something very similar, except for rather than trying to calculate apply the percentage distance between 2 distances, instead we are going to be applying that percentage to the coordinates from the first point to the second point. So if we do that again, obviously the maths ends up being that it's halfway between both the x and y points, and we get our final coordinate, which is 1520 in this case. And we can simplify all of this a bit to effectively instantly calculate the distance just by using the time and distances of the surrounding stations. And then we can work out the x and y coordinates using the bottom equation, where we're inserting using the previous and end x and y's positions. This is effectively all we need at this point in order to fairly accurately represent the coordinate positions of our vehicle at any time. With these formulas, we now have the power to, from any GTFS static data on our server, work out where we expect the vehicle to be. But we can do better. We can apply GTFS-Realtime data to improve this information by making use of 2 elements. Firstly, delay information, where delay information is going to let you know how far behind on schedule a vehicle is. So it will say 2 minutes behind for this trip, and it can also let you know delays for specific stations. So we expect this train or this vehicle to arrive a minute late to just this station, or a minute early at this station. And this is really easy, wonderful information because it works perfectly with our formulas, because all we have to do to consider these delays in our calculations is take the delay, apply it to the time we're interested in, and then run those equations. And it's as easy as that. You then get a result out, which then represents our predicted position, which is wonderful. I love it when it's simple like that. What's more interesting, however, is actual live vehicle position updates. So these, although not commonly used, allow us to start actually formulating a much more complete image of the rate of travel and positions and expected positions of vehicles at any time. Because if you think of one of those networked maps, transit lines that we were looking at before, such as one of these, if you think of stop 2 and stop 3, the kind of almost certainty of a vehicle's position is almost 100% at each of the stops, especially if we have delays accounted for. However, the further away you get from any stop, the less certain we are of the actual position, because we can't account for vehicle speed, we can't account for vehicle having to stop for traffic and traffic jams and various other things which can affect rate of travel. So what we can do with vehicle positions is start to try and fill in the gaps between those two nodes by effectively inserting more nodes with times attached between them. And obviously we can't just watch one trip, see at the minute intervals where the vehicle was, insert them as nodes and call it a job done, because chances are that single trip isn't going to be representative of every single day and every single time that trip has ever travelled. You're going to need to work out some more accurate ways to create a representation of the average speeds and positions and times of the vehicle at any time. So you should effectively use some form of averaging algorithm in order to establish how likely you expect one of these inserted nodes to be accurate, which then allows you to slowly morph the times and positions of these different nodes intersecting the two stations' positions until, over a period of time, depending how accurate you want to get, you have a fairly accurate representation of the position of the vehicle throughout the entire process of travel. And with that information, if you have it available, you have a very accurate representation of a vehicle, and any vehicle in the entire network, which is brilliant. And we now have the vehicle positions at any time. But we're not quite done here, because if, let's say, my global vision of representation of all vehicles in the world, and we want to send that to clients to render, wonderful idea, but we're going to be sending thousands and thousands of updates to them at incredible rates. Let's say I want really real time, so at least every half a second, say, like minimum representations of the vehicle positions. So sending thousands of messages every 0.5 seconds to every single client subscribed. That is not scalable. That is going to consume all the bandwidth of these devices. Nothing is going to work. We're going to be having a terrible, terrible time. So we need to work out how best to then actually convey this information now available on our server to our JavaScript clients to render. So how do we break up this data? Two major ways which I've used is one, attempting to reduce the number of messages by containing more information within each message, and secondly, trying to then break up the different transit systems and regions of the map into different channels, where, just for anyone not familiar with pub-sub paradigms, a channel is effectively something which a client can subscribe to and a publisher can publish data to, and allows clients and publishers to effectively break up the information into different buckets in which people can indicate what interests they have. So you could have one which is for, I'm interested in American data and I'm only interested in UK data, and then people who are interested in those bits of data subscribe to the relevant channel, and publishers with that data publish to the relevant channels. So looking at how we can represent the trips data in a less message intense way, one thing that we can do, and I did do in this case, is make use of spatiotemporal updates, which is just a fancy way of saying positions with times associated with those positions. And what we can do is effectively have a message which contains various nodes, as very similar to effectively what we saw in the GTFS data itself, nodes and times associated with those nodes for a period of time, let's say a minute, representing then the expected position of a vehicle between those times, and then allowing a client to easily interpolate the expected position of a vehicle between those positions to represent the entire travel for that small period. So how wide you want this time period to be is entirely down to your use case and how much data you think your clients can handle and how regularly you want to be adjusting things. But in general, let's say a minute is a good window. So a minute, an update a minute per vehicle seems reasonable to me. And if you look at this is just an example of a bit of spatiotemporal data where you've effectively got the time associated with some coordinates, and just a whole array filled with that represents the entire route of a vehicle for that period. What we can also then do, going back to channels, is make our channels grouped up based off of zoom level and then which region of the map you're interested in within that zoom, where effectively how you can imagine the zoom levels is that it is broken up into little squares. So if you're fully zoomed out, you have a single big square. However, if you effectively have your map broken up into 4 sections, which is referred to as quad tree, where you continue to divide that map up into further 4 sections each time you increase the zoom level. So at zoom level 0, you're showing the entire map. Zoom level 1, you'll have something like this, where it's divided up into 4 sections. And then, again, repeat, zoom level 2, break up in each of those sections into 4 sections. That's following a quad tree. And continue like that, where then, if you look at this, what we have is a bunch of different sections at zoom level 2, and we could refer to one of these little sections as, say, the bottom left corner could be 0, 0, next one to the right could be 0, 1, 0, 2, 0, 3, all the way up until the top right corner where you'd be at 3, 3. And then by subscribing to this information, you could have only information within the specific section you're interested in, which can be great because often you won't want to have a client receive all information of the entire globe at once. Chances are you want people to be able to zoom into sections, see all the vehicles moving about, zoom out, get a more abstract representation of this information, and zoom in somewhere else and then get information about that. So you can quite easily work out what section you want to both publish into as well as subscribe to just by applying a bit of this formula effectively to the coordinates that you're interested in, and subscribe to that channel or publish to that channel. And this is really useful for me personally because Mapbox, which is what I've been using for rendering, also makes use of these quad trees in order to divide up based off of zoom. So it just makes it compatible for me basically. There's also just the general idea of making more zoomed out channels contain lower levels of fidelity of information and going away from representing exact vehicle positions to representing more generic information about transit systems. Because if you think of being zoomed out on the entire world, if you were to view the transit information of a single city and you want to draw every single bus and train of that city, then all you're going to get is a big blob of the vehicles and you won't be able to distinguish anything and it will be useless. So really, what you're wanting at that stage is to probably provide more metadata around it. More, how many vehicles are there? What is the general delay status of all of these vehicles? Any form of information you might be interested in. And then as you zoom in, you start providing more specific information. So perhaps rather than showing every single coordinate of a transit vehicle going about its day, as you zoom in a bit, you instead getting a more high-level representation, only showing the start and end points of a transit vehicle travelling between 2 points at a zoom level of, 5, let's say. But then until eventually you're at a zoom level where it actually makes sense to have accurate representations of the vehicles, and you're done. Let me discuss just very briefly how I went about actually rendering the vehicles, which is effectively very simple from the client side. All you need really is to connect to the Ably Hub product, which is publishing out all these messages, which for that I just use the Ably.js client library, and then effectively just rendering those positions that are sent to our JS app using Mapbox, which is effectively just using the coordinates, the times, and interpolating between the points based off of the times. And by doing that, you end up with something like this, where you just have your vehicles moving about, going about their business, and you can, effectively just have a bit of fun with that. There's a link on the right where it's hosted. There's a couple different web pages which I'll include as links probably in the chat. But yes, thank you so much for listening to my talk. This was a pre-recorded talk, but I will hopefully be in the chat to answer any questions that anyone has. Thank you so much.
What a great talk, Tom. It's so interesting to see how it's possible to use real-time data to get better user experience. And now we're all so busy with our lives that we want everything like right now rather than being out of date. So that's just awesome. I think people are definitely going to be using real-time data more, especially because you used that concrete example. Everyone, don't forget to go follow Tom on social so you can keep up to date with the awesome work that he's doing.